Hello, and welcome to this tutorial about Feynman diagrams. We've talked about them in the lecture notes, but we want to see them now in the board to see if we understand the concept. So let's start with the topic. And we've seen in the notes that we have a Fermi liquid when we can describe our Hamiltonian of the system as a non-interacting part that we call H naught times another interacting term. And we've seen in the notes that this interacting term, this operator, can be expressed in terms of the creation and annihilation operators as a sum in different momentums. And then we had the matrix element times the creation operator, another creation operator, and then two annihilation operators. So that was our interacting term in the Hamiltonian. So the thing about Feynman diagrams is that they are a way to describe interactions between particles in the system. And precisely this term can be described as a Feynman diagram because it's an interacting term and we have two creation operators and two annihilation operators. How do we describe that as a Feynman diagram? So to do that, we have something like this. You've probably seen that before, and it's quite common Feynman diagram where two particles interact by a particle here, interchange of a particle. So we have a particle with K1 and another particle with K2 coming at some time, and time is running up in this picture. And at some point in time they interact and they exchange some momentum Q. So from this particle, momentum Q passes to this one, and what we have is now a particle with momentum K2 minus Q because we've lost some momentum, and a particle with momentum K1 plus Q because this particle has gained this momentum. So this is a simple example of Feynman diagram describing this term, and this term here is called the vertex interaction. So this is what we call vertex. And it has to be with the strength of the interaction between two particles. In our case of the Fermi liquid, we said that this vertex is related with the Fourier transform of the Coulomb potential. So depending on the physical potential we have, we will have different vertex depending on the potential we have. So for example, that's not an example, but having that, we can integrate in space times e to the QR the potential depending on position. So this is the matrix element BQ. Okay, so but we want to use these Feynman diagrams in our perturbation theory in the many-body physics frame. So how do we do that? Okay, so we have the Fermi liquid. We've seen in the lecture notes that perturbation theory, ordinary perturbation theory, is not correct when we are talking about many-body physics, because we have to deal with all the many-body states, and then it's not something suitable to do. So instead, what we have is a perturbation expansion using time. And to use the perturbation expansion using time, we have in the lecture notes the expression for the one-particle Green's function. The one-particle Green's function, remember, that was defined between time t and t dash as this thing, as a zero temperature. So we have k and t and ck in t dash dagger. So it's an average value between the creation and annihilation operator between the ground state of the system. And this is easy to evaluate in the non-interacting case, and this is one of the exercises of the lecture notes. So in the non-interacting case, what we call G naught of k, and then we Fourier transform to energy space, frequency space. So basically what I'm doing here is nothing but integrating in time e to the I omega t times G naught of k t minus t dash, and this is in the exercises. But if you've done the exercise, you should arrive at some expression for G naught of k omega that looks like that for the non-interacting Fermi gas. So this is something like this. So it does depend on the energy of the particles. So depending if we have positive energy, we're talking about electrons because we are above the Fermi sea, whereas if we have negative energy, we're talking about excitations that are holes. And this is the expression for the non-interacting Green's function. But this is a non-interacting system, and of course it's not considering the interacting part we were talking about before. So how can we insert that, and how is this function going to change when we do that? And we've seen that the perturbation expansion for the interacting Green's function, this is the total Green's function, not the non-interacting one, so the same I have here above. We've seen that there is an expression for that in terms of the perturbation expansion. So we have n0 to infinity minus I to the n divided by n factorial, and then we have a set of integrals. So depending on time 1, integral time n, depending on the order of perturbation we want to calculate. And then I'm gonna erase here better. And then what we have is the S matrix. We were talking in the notes. So the S matrix between this ground state average. First we have the CK at time t, and then we have all the interacting terms at different times. So we have Tn till T1, and this is the interacting, and then CK dagger T dash, and then we average, of course, in the ground state. So this is the expansion for the S matrix, and this is the perturbation expansion in the many-body basis. What we have to do is to evaluate these brackets for all the orders of perturbation we want to work, and we've done that in the notes, and we've arrived for an expression for the first order correction of the Green's function. So let me continue here up, where we can now start using what is in the notes known as the Wick's theorem. That says that, imagine we have some interaction term as we had before, like it's going to be summing K1, Q, and K2, and this is going to be PQ, CK1 plus Q dagger, CK2 minus Q dagger, CK1, CK2. The fact is that because we are working in the interacting representation of quantum mechanics, all these operators now depend on time, but they are free propagating, so they propagate freely. That means that we can act with these operators over the ground state of the non-interacting system, because then this is an average, we know. Those are just the Green's functions we've worked out before, and I'm going to write them here for as a reminder. So this is 1 over omega minus this plus I delta sine of this. Basic definition of non-interacting Green's function. So we have this interacting term, and we want to calculate the first order of interaction. Okay. So the first order of interaction, G1, we've done that in the lecture notes, but this is going to be something like this. So it's minus I squared, and then we have an integral in the time, intermediate time, and then we have this to evaluate these brackets. So CK of t, and then we have CK1 plus Q dagger, CK2 minus Q dagger, and all these operators I'm writing here, CK1, CK2, all these operators are evaluated at time t1. And then I have CK, let's call it K, yeah, CK dagger at time t dash. And I'm averaging respect the ground state, of course, of the non-interacting system. So this has to be evaluated now, as we've said in the notes, using something that is known as the Wick's theorem. I'm going to erase the general expression because it's not useful for us anymore. But this is the quantity we have to evaluate, GS, and then we have the time ordering operator that you also have the definition in the lecture notes. ck1 plus q dagger ck2 minus q dagger ck1 ck2 ck dagger t dash, and all these operators are in the time t1. We shouldn't forget that. Okay, and this is an average respect to the non-interacting system. Okay, so how do we do that? So Wick's theorem tells us that we compare all the creation and annihilation operators in parents of non-interacting Green's functions, and this is equivalent to this. So one of the possible parents we can have here is pairing the terms as we have them. That means I'm pairing this term with this term, this term with this term, and this term with this term. And this is something we've done in the lecture notes. So Wick's theorem tells me that this is equivalent to having GS, T, and then we have CK of T, CK1 plus Q dagger of T1, okay, and I close the average. I'm not going to use anymore the ground state because it's totally understood that it's an average respect to the non-interacting ground state. So if you want, we can use that notation here. And then we have 0 and then another time ordering operator, and we have this CQ minus CQ's CK2 minus Q, sorry, at T1, CK1 at T1, 0. And then we have another one, the last one, which is CQ at T1, CK dagger at T dash, 0. Of course, this old term, well, this has a sum in K, K1, and K2. And also the minus I squared here. So how do we evaluate that? Now that those are just non-interacting Green's functions, but we know that within a non-interacting system, momentum in the Fermi liquid has to be conserved, in the Fermi gas has to be conserved. So that gives me a condition here that K2 has to equal K, and then this condition here provides that if K2 equals K, then I have here K minus Q equal to K1, okay? And then I have here that K has to equal K1 plus Q. Or in other words, K1 has to be K minus Q here, and here K1 has to be K minus Q. So we see that this is exactly the same condition for the momentum K1, which means that we get rid of one of these K momentums, because the K1 can be substituted by K and Q appears here. So we only end up with a sum in Q, because K is already there. So, and K2 equals K. Okay, this is just a pairing where momentum has to be conserved, and you can do that explicitly. But the important thing here is, how does this look in a Feynman diagram? What is that how can we express that as a Feynman diagram? And that's what we want to do now. Okay, I forgot again to put here the vertex interaction, of course. Okay, so that's the first order of perturbation. These are my weak contractions, and then I want to write the Feynman diagram representing this first order correction. Okay, I'm going to leave that there, because this is the Wick's contraction we have. And I have first a non-interacting Green's function with momentum K1 as K minus Q. So that means if K1 equals K minus Q, then this is just a Green's function of momentum K, and then propagating between T minus T1. This other term is another non-interacting Green's function, so this is times this non-interacting Green's function in time T1, okay, where momentum is now, if K2 equals K and K1 equals K minus Q, then this is K minus Q. And then we have momentum is between T1 and T1, and we've seen that in the notes this is expressed like 0 minus, which means we approach T1 from the right, and the operators have to be normal ordered. Okay? And then at the end, the last term is just a Green's function, non-interacting Green's function between k2 and k, but k2 has to equal k to be non-zero, so this is between t1 and t dash. Okay, but it's more important here, we can represent that as a Feynman diagram, where we have the following thing. A line, first line, and we have t as our end time and t dash as our time at the beginning, but it doesn't really matter because remember that we have here the time ordering operator, so we can in fact study what happens if we invert time, so when t is greater than t dash or t dash is greater than t. But then we have an intermediate time t1, but we know that here, because we have the non-interacting Green function of k minus q, this term is losing momentum, so this Green's function has to lose some momentum in t1 and then recovering it here again. So this is t1, t1, but some momentum is lost here. Well, momentum q, so we start with a momentum k for the first Green's function, which is this one, the non-interacting one. And we arrive at t1, and one momentum q is transferred because the next non-interacting Green's function has k minus q. And then at the end, when momentum comes back, then of course this recovers the momentum k. So we have that as the and this is our Feynman diagram in momentum and time representation. Another thing we can do is to represent this diagram instead of momentum and time in momentum and energy, just by Fourier transforming the expression we have here. So this will be one of the corrections we can make, but we've only done one of the possible pairings we can do. What is the other pairing we can do in this expression? Because we've taken the operators as they stand, but we could have chosen another one. For example, let me now erase that. So we've seen that our first correction has a Feynman diagram of this type if we choose the operators to be in this order. But what happens now if we instead take, for example, this, we put it with this one, okay, and then we match this term with this one here, and then we have these other terms there, the other terms there. Well, then we have another weak contraction because I can swap the fermionic operators between them. However, remember that if we swap two fermionic operators, there's always a -1 sign appearing because of the anti-commutation relations. So you have to be careful when you do that already. I'm not going into the detail of the calculation because this video can't be very long. It will be a good exercise for you to do it on your own. But I'm just going to say that we've discovered with that using Wick's theorem and Wick contractions, we can, in first order of perturbation, calculate the correction for the single particle Green's function, or what is the same, how does this non-interacting Green's function change when we add the interaction or the perturbative term, this one. And in first order, there are basically two diagrams we have to consider. First is one diagram going this way, and the other one is the one we've just seen here now. So the order of the arrows doesn't really matter because it depends on how you want to, what is your criterion for time propagating. But this term here is called the Hartree term, and this term here is called the Fock term. I would say that here the most important term of both is the second one, this one we've derived here, because it's the one that appears frequently in calculations, whereas the Hartree term usually can be just regarded as a renormalization of some local chemical potential or something like that, because we have just here a loop. So basically there is no momentum transfer here, because if this goes with momentum k and this goes with momentum k, then q here has to equal 0, and that's something we've seen in the notes before. But these are the two terms in first order of perturbation, and these then in Dyson's equation, we've seen Dyson's equation as g naught of k omega plus, and then we have g naught, something we call the self-energy, and then g of k omega. That means that the self-energy is something we don't know in all orders of perturbation, but we can start adding terms in this self-energy considering just the diagrams we have here. For example, here the self-energy will only consist of these two diagrams because they are the two connected ones, and remember the definition of self-energy is that energy that terms that contribute that can't be split into two independent diagrams by cutting one line. That means that if I have a diagram we're going to see later in second order of perturbation, something like that, this is of course a non-self-energy term because I can split the diagram into two by cutting the line there, and this is not going to contribute to the self-energy in the expression. But I can have second order diagrams where this can't be done. For example, the most common one you will see in Feynman diagrams in second order of perturbation is called the loop diagram, or the bubble diagram, where you have this expression for the interaction in second order. So in first order of perturbation you always have in Feynman diagrams one wiggly line which is representing the interaction. If you go to second order of perturbation then you have two wiggly lines. If you go to third order you will have three wiggly lines, and so on and so forth. But what interests us is a method to calculate this diagram, or visualize them at least. And I haven't explained that to you, and that's what I'm going to do now in these last minutes of the video. I want to explain to you how to calculate Feynman diagrams, at least not technically, not all the mathematics, which are just Fourier transforms and weak contractions. You have to be careful to see which creation of